In this chapter, we'll be discussing work and energy. So to begin with, we'll talk about work, and the definition of work is the product of force times distance, or the formula W is equal to F times D. Now the units for work are going to be newtons, units of force, times meters, which is units of distance, but this is given a new name, a joule. So a joule is equivalent to a newton meter, which is the units of work. Notice that motion has to occur in order for work to be done. There's got to be this distance factor. So, for example, if you are holding a package in your arms for a period of time, and the package is not moving, even though you might be getting tired, there's no work being done on that package because there's no motion. When you picked it up from the ground, then there would be work done because there would be a distance involved at that point. Now, a closely related concept is that of power. And power is defined as the rate of doing work. And so power is equal to work divided by time. The units of power would be the units of work, which you've already said is a joule, and of course the unit of time is the second. And we further define that unit, the joule per second, as a watt. Now, one of the things is that there's often a lot of confusion between work in joules and power, which is in watts. Remember that power is the rate of doing work. But if you're talking about a quantity of work, then the units here must be joules. Okay, now we move on to energy, and specifically we're going to be talking about mechanical energy. So when work is done on an object, the object gains energy. And when the object has energy, it now has the ability to do work. All right, now, so there's a couple of different kinds of mechanical energy. We're going to talk about first potential energy, and this is energy an object has because of its position. There's actually a few kinds of potential energy as well. We're going to stick to talking about just gravitational potential energy in this chapter. And gravitational potential energy is when you are doing work to elevate an object, to pick an object up some given height. The formula for gravitational potential energy is mgh. In other words, the mass of the object times g, remember, is the acceleration due to gravity, 9.8 meters per second squared, times whatever vertical height the object is lifted up. So, a simple example might be if you've got a 2 kilogram mass elevated a distance of 10 meters from the ground, that would be the height, then the potential energy would be approximately 200 joules. In other words, 2 kilograms times 9.8, which is approximately 10, so that product would be 20, times 10, which is 200, and the units, of course, would be joules. Now, the other kind of energy is kinetic energy, and kinetic energy is energy of motion. Formula for calculating kinetic energy is 1/2 the mass times the velocity squared. The units of kinetic energy are also joules. So now, work, potential energy, and kinetic energy all have the same units, joules. Now this v squared term is pretty important because if you notice, if the speed of an object is doubled, in other words, that would be the v term here, then the kinetic energy would actually be quadrupled, 4 times the value, because of this v squared. So that's going to be important, as we'll see in the next slide. Suppose this speed is tripled. What would happen to the kinetic energy? How much would it increase? Well, the answer would be it would increase by a factor of 9, again, because tripling the speed is multiplying it by 3, and when you square that, you're going to get 9 times the value of the kinetic energy. Okay, now, very important concept here, the work energy theorem. Work energy theorem states that when work is done on an object that causes the object to increase in speed, then the change in kinetic energy is actually equal to the work. The work is equal to the change in kinetic energy, better way to say it. So, for example, if you do 10 joules of work on an object and you cause the speed of that object to start moving, increasing, then you know that there's going to be an increase in kinetic energy of 10 joules. Now, friction can do work on a moving car. We learned before that friction always acts opposite to the motion of an object. So in that case, then friction is actually decreasing the kinetic energy of the car. So the work due to friction causes a decrease in kinetic energy. Now, this is useful in measuring stopping distances for cars. So, for example, if a car is traveling at 60 miles an hour and it jams on its brakes and skids, then the road friction is doing work against the car, and the amount of work that the road friction does is equal to the actual decrease in kinetic energy of the car. Now, if the speed of a car doubles, then that means that the stopping distance is actually going to increase by a factor of 4, and here's the reason why. We learned that if the speed of the car doubles, that means it's got 4 times as much kinetic energy, which means there must be 4 times the amount of work required to stop the car. And since work is force times distance, force due to friction in road friction is pretty much independent of the speed of the car. So therefore, it's the distance that's going to increase by a factor of 4 in stopping the car. Speed of the car triples, then the stopping distance is going to increase by a factor of 9. Okay, now conservation of energy says that energy cannot be created or destroyed. This is probably the most important principle in all of science. You can transform it from one form to another, but it can't be created or destroyed. Okay, so here's an example. Take a basketball, you throw it up in the air, you let it rise, and it comes to a momentary stop, and then it falls back to your hands. So when you throw the ball up, the basketball has kinetic energy. And as the ball rises, its kinetic energy is decreasing until it reaches the maximum height, at which point its velocity is 0 and its kinetic energy is 0. But all during that time it was rising, the potential energy was actually increasing because the vertical height was getting bigger. Okay, so then the ball starts to fall down again, and as it falls back down again, its kinetic energy starts to increase because it's moving faster and faster, but as it gets closer to the ground, its potential energy is getting smaller and smaller and smaller. So all during that whole interval, the total energy, the sum of the potential and the kinetic energy of the basketball was actually staying the same. At the point where it was just thrown up, it was all kinetic. At the point where it reached maximum height, it was all potential. Okay, now, machines, simple machines like an inclined plane, can actually multiply force, but at the expense of distance. So the total work required to push an object up an inclined plane is the same as it is as just lifting it directly up. But the force is smaller because the distance traveled is going to be much larger. And there's a better and more thorough explanation of all this in your textbook, but the point to remember is that Machines, like inclined planes, multiply force at the expense of distance, but the work required is the same. Machines cannot uh, increase or decrease or change the amount of work required to move an object. So a lever is another good example of a simple machine. I'm sure you've all used a lever at some point or another to pick up a rock, pick up a heavy object. It multiplies force, again, at the expense of distance. So you've got to push down a relatively long distance to get the object to move up a small height, but on the other hand, it allows you to apply a much smaller force. A bicycle, on the other hand, works the opposite way. It multiplies distance at the expense of force. So we ride a bicycle and we can go a whole lot faster than we do if we just walk, because when we apply a force at the pedal, it multiplies the distance as the wheel spins around. Now, the efficiency of a machine is the energy out divided by the total energy, or the total energy input. And the efficiency of a machine is never quite 100%. We never get exactly the amount of energy out as we put in. There is always some losses due to heat or friction. Now, some machines tend to be pretty efficient. Lever is a good example. Not much friction there, but there always will be a little bit. And so we never get exactly 100%, and certainly we can never get more energy out than we put in. All right, well, energy is a topic in the news because of the fact that, as you know, we need energy for all the various things in our day-to-day activities. And we get energy from fossil fuels, which includes oil and coal, and some cleaner energies, solar, wind, and nuclear. Fossil fuels, as they burn, unfortunately, produce pollutants in the air and carbon dioxide, which accumulates in the atmosphere and contributes to global warming, the greenhouse effect. We need to put a bigger emphasis on the cleaner energies like solar and wind. Actually, wind is really just a kind of solar, but the energy from the sunlight that falls on the earth is, if we can only harness it effectively, we can use that for most of our energy needs. Nuclear is another source of energy, but unfortunately that comes with a whole host of problems as well. Now, since energy is such an important issue on our everyday lives, there's a lot of what I'm going to call junk science related to energy. Remember that there's no such thing as a perpetual motion machine. You can never get a machine that's got an efficiency of exactly 100%. If it looks like it's a perpetual motion machine, look closer, because there's got to be energy input coming from somewhere.